So here's the problem. We haven't really solved the problem of trillions. This is a hard problem. But a wise man once told me that if you want to solve a really hard problem, go find someone else who solved something like it and see what they did. It turns out nature has solved the problem of trillion. My body, 7, 8 trillion cells. I don't reboot every month. I'll go maybe 80 years at a clip, right, if I'm lucky. Well, I won't, but some people will. I eat chocolate a lot, sugar. So if you think about it, right, humans are computing systems in their own right? And you know, they display information, they store information. What's one of the patterns we can find that nature did? Well, they have atoms, and those atoms make up molecules, and the molecules make up cells, and then those cells make up organs, and then the organs make up systems, and then those systems make up me, and then like you and I together, we make up us, and then a bunch of us together make up a community. So this is this really interesting design pattern, and it's a design pattern you find in nature. And that design pattern is called layered complexity. That means the things at the low levels don't need to know what they're going to be used for, the things at the upper levels. The atom doesn't know it's going to be made into a molecule or made into DNA, and the molecule doesn't know it's going to be made into a cell or something like that, right? This is semantic layering, they call it. It's mostly hierarchical in nature, not completely. But it's a design pattern that if you pay attention to it, you can build resilient systems. And it's just something there that if you study nature, which is the most advanced I can find, you're actually going to find out some things. So let me just posit this. Trillions is the future. It's coming, whether you like it or not. You know, if we were to flash forward and look at the day that kind of scale comes, we would find industries gone. We would find entire new industries overnight. Here's an example, right? 300 billion power outlets. It turns out that analysts calculate the number of sockets and light switches and lights in the world, and every 10 years, about 300 billion of them get exchanged for new ones because of renovations and new building construction. If you took a percentage of those and just made them wired, just put them on the internet, you could lower energy consumption between 40 and 60% because you would suddenly create a feedback loop. You know, just like the Prius, right? You're driving the Prius, you see you're just on the electric side, you take your foot off the gas so you won't go into the gas side. Networks generate feedback loops, and it allows you to actually tune your responses. I put my hand on something hot, I take it back. Right? That's the way the world works. And so we'll do it because there's a huge opportunity to do this. I've been working with a company in the UK that makes little chips to go into power outlets. They cost less than $10. They put you on the internet. They sample at the same rate as a utility. So if you plug in a copier and you make a color copy, it knows you made a color copy from the signature coming out of the electrical thing. If you make a black and white one, if you make a single copy, a double-sided, if you use thick paper or thin paper, it can tell just from that signature. So there's a lot of information we can harvest if we do this. So, you know, layered complexity is sort of one of those design patterns. But it turns out there are design patterns all the way up nature's kind of ladder. And I'm going to talk about a few of them. Right down here at the very bottom is something called unique identity. So in the physics layer, it's sort of the layer of the universe, before we even get to biology, we actually find something called unique identity. No two atoms can exist in the same place at the same time. That means when you and I are talking about a can of cola, we both know we're talking about the same things, because two of them can't be in the same place at the same time. That's pretty convenient, because you and I can have discussions and we know we're talking about the same thing. But if I say Moby Dick, what am I talking about? You know, information doesn't have atoms. It doesn't have, you know, Pauli's exclusion principle working for it. So what do I mean when I say Moby Dick? Do I mean, you know, this book? Do I mean all the books Moby Dick? You know, do I mean the pattern inside the book? Call me Ishmael. It turns out that many arguments really turn out to be confusion around identity. We think we're talking about the same thing, but we're not. And as we start connecting all this stuff, it's going to be really important to know we're talking about the same thing if we're having a conversation, especially if we're making decisions, especially if we're making business decisions. So universally unique identity. Without it, it's kind of like the blind men all trying to describe the elephant. Right? One of them is saying, I've got it, it's a snake, while he holds onto the tail. Right? Another one holds onto the leg and says, it's a column. The other one pats the belly and says, it's a wall. Right? We all think we're talking about the same thing, and we're not. We actually see this today in all of our blogging and all of our you know, news channels and all those other things. We think we're talking about the same thing, and we're probably not. This is a universal unique identity. This is sort of mathematician's solution for atoms and Pauli's exclusion principle. It's just a really big number. And mathematicians will tell you that really big number, you are guaranteed it is unique in the entire universe. So you can use it. It's just a big number. But you could number every atom in the universe, you'd have numbers to spare. So this is how mathematicians solve it. And they're starting to use this in some places. So it's a pattern that now has gone from nature into computing. If you were to go up another level, you'd actually find other patterns. Down at the chemistry level, there's something you start to see called architecture. This is really fascinating. So Mendeleev came up with this idea for this thing called a periodic table. You all probably had them in your schoolrooms when you were growing up, but you didn't know really what they meant. He found the hidden architecture of how molecules recombine, how elements recombine and form things. And architecture is interesting because architecture with a capital A gives you predictability. It gives you future-proofing. If you figure this out right, you can predict things 100 years into the future. And if you're trying to be a good designer, you're trying to be a good innovator, it's nice if you could predict things. It's like knowing the shape of the whole iceberg when everyone else just sees the tip sticking out of the water. So this is interesting. It turns out that the ones in gray he discovered back in the 1800s. The ones in the lighter color green were discovered in the 1800s, the early 1900s. Some of these weren't discovered until a few decades ago. So he was able to predict a whole bunch of stuff. And in fact, when Ica aluminum, which is what he called it, was discovered, he predicted in 1871 that there would be an element that he didn't know what it was, but he said it was going to fit right there, it was going to have these properties, etc. In 1875, a Frenchman discovered it. He called it germanium. He said, this is how much it weighs, this is what's up. Mendeleev said, you're wrong. It doesn't weigh that. It can't weigh that. This is where it fits. And there was a huge debacle, international debacle, because clearly Mendeleev was off his rocker. Right? This guy had found this new element. He had measured it. Turns out he was wrong. Mendeleev was right. Germanium, interesting thing. He predicted it 4 or 5 years ahead of time. It's what's in just about all of our semiconductors, right? Germanium arsenide is like the thing that we make semiconductors out of. So architecture, if you can study the underlying patterns, you can do an awful lot. And that's a design pattern from nature. You can go up. You know, if you were to move up, there are a ton of others. I just won't touch on them. But you go to biology, and things get really interesting. So there are a whole bunch of design patterns. I'll talk about a few. I'll talk about containerization. This sounds really boring. I know it's near the end of the day. You're like, he's talking about containers. DNA is the standard container for life. It's the sort of the bundle that holds all the genes. And it's not just life like humans. It's life like all life. Chromosomes, right? They kind of bundle up these things. What is DNA doing with this containerization? It turns out it's got a unique identity. It's made of atoms. It's a standardized container. It can be used for everything. It's mutable. You can glue new genes on and come up with whole new things. So it allows for evolution, it allows for genetic diversity, it allows for new ideas. Containers kind of sound boring. Let me talk about this one. This is more exciting. This is a shipping container. It turns out the invention of the shipping container, mirroring what happened in life, led to an explosion of commerce. Pretty boring, right? But it's got a unique identity. It's mutable. You can load things in and load things out of it over time. If you think before shipping containers, it was actually longshoremen piling things into boats. Very tedious. You had to make sure not to put like the anvils on top of the bananas. Right? But once they invented shipping containers, suddenly you didn't need to know anything about what was inside. All you needed to know was the dimensions. You could build a ship, you could build a crane, you could build a truck. Explosion in commerce. In fact, the decade that shipping containers come into play, we had the increase in trade more than twice as fast as the manufactured goods being manufactured, and 2.5 times the global economic output. Just the institution of this one design pattern from nature made this explosion. It's part of what flattened the world. There was not much global trade happening before standardized shipping containers. So not very sexy, but it's a design pattern. And you can find others. Liquid currency was a really big design pattern that happened in nature. You can't get really far in economics if you try to trade like, 2 lambs for 3 rolls of cotton or something like that. It's not scalable. It doesn't interoperate. It's very hard to separate the value from the actual thing. It's my sheep, man. Give me money for it. But the idea of a liquid currency revolutionized economics. This was a big deal. In fact, does anyone know, I'm going to stick on this for a second. Does anyone know who presided over like the Bank of England when they started thinking about liquid currency? Anybody? This is back in the 1600s, late 1600s, early 1700s. Huh? No, he probably built it, though.
Isaac Newton?
He was Isaac Newton. Right, so Isaac Newton, a guy who called himself a natural philosopher because he studied nature's patterns. They didn't have the word scientist for 100 years before that, after that. He was put in charge of the Bank of England, and for 150 plus years after that, England dominated in terms of the currency. Right, this one little design pattern took advantage of it. Liquid currency. Nature does it. They don't call it, the gene pool for nothing. It's incredibly liquid. Craig Ventnor, the guy who went and sequenced the human genome, brilliant guy. He went and took barrels, 5-gallon barrels, and started scooping them up out of the sea on this ship, this research ship he called, like the HMS Beagle 2 or something like that. And he started scooping up barrels of water, and he started straining them and sequencing anything he found. And it turns out that before he did that, people thought that the pigment that encodes your blue eyes, the gene that encodes that, was only really around in 2 other organisms. But after he did this, he found they were in 80% of all the organisms. They were used for photosynthesis, they were used for energy production, etc. So this recombination was crazy. You've probably heard of the Cambrian explosion. Pretty great innovation event for nature. And it came about because we agreed on this kind of liquid currency and we share it everywhere. That's why you can have transgenic goats that make human milk, because it's the same currency. Also easily replicated, right? You can just use cell division to make replicas. You don't need a giant server farm. You don't need huge infrastructure to move these containers around. So the question I would ask is, does that even exist in computing today? Do we have a standardized shipping container, a common currency, liquid, mutable, etc.? It turns out, I've asked a lot of people, and the answer is no, we don't. And yet every complex, rich ecology, every system that we've ever been able to find, nature, does. There is some kind of liquid currency at the lowest level of computing, bit and byte. The packet, the internet, incredibly good. In fact, these 2 layers are probably the biggest sort of generally new inventions that mankind has made. Moore's Law and all the rest. This stuff masks the fact that there is nothing at the web level that actually supports this. There is no unique identity. There is no liquid currency. We are building new silos and we're calling them apps. And it's horrible because it's unlike anything found in nature. So design patterns are interesting in that if you know them, you can predict things. You can see into the future. You can design 5 degrees different and actually set yourself up to succeed when others fail.